Also, don't forget you want to get this formula down. Percent error equals the theoretical, which is the number I gave you, minus what you got in the laboratory. And that's absolute value. That's what these lines mean, divided by the theoretical, which are these numbers right here, times 100. That gives you your percent error. So make sure you have that for the laboratory. All right. Other thing we want to do today is we want to finish our talk about concentration with solutions. We want to do a dilution. Dilution. See if I got the right text here. Here we go. All right. So today's problems we're working on are dilutions. So you need to know the notes from page 16. I'm sorry, page 6. While you're all getting to there, let me go ahead and get attendance real quick. Make sure we got everybody. Let's bring this out here. So that's kind of right there. Boom. All right, attendance for period 3 by name. Let's get the in-person. Henry, Seth, Batavia, Anthony, Tony. All right, so there's our in-person. Let's check out home. We've got Kaya, Amara, Childs, Lauren, Emily, Josh, Omar. No Omar? Tori is out there. Kincaid, Anna Kincaid, Maggie Kincaid, yep. Bella goes by a different name. What is it? It's been a while since I remember. Bella, what is the name? You go by Jay, that's right.
It's Jay.
Yep, Namara. Micah. No Micah. Nick is there. Sanchez there. Katie. And Stewart. I don't see Stewart. Oh, there you are, the seal. Good. All right, cool. So we got that out of the way. Let me make sure I got all the virtual students marked correctly. Last chance real quick, Omar and Micah. Those are the two I have absent. All right, cool. Let's take a look at the math behind this. So you live in a world where everything is pre-measured. We even have these things called Tide Pods, right? You guys remember a few years ago, the Tide Pod Challenge. Maybe you were too young or whatnot. But basically people were trying to tell people to eat these little Tide Pod things. That's a joke, because if you actually were to eat one, it could do what to you? Kill you, right? Why could this kill you? Louder? It's not just regular soap in the Tide Pod either. Yeah, right. It's all about concentration. Tide Pod is a very small thing that's very highly concentrated. The idea is that you can put one of these little tiny things into an entire washing machine filled with water, and that's still going to be able to clean those clothes. It's a very high concentration. How much water is in your mouth compared to a machine? A lot less, right? How about your throat? A lot less. So this high concentration, this particle is then going to, as your mouth dissolves the plastic of the, well, it's not plastic, but the outer edge of the Tide Pod, that chemical is going to leak into your mouth, and it's not going to be dilute at all. It's going to be highly concentrated. It's going to then react with your cell layer, and it's going to break it down in a reaction we call a caustic reaction. Caustic. As acidity or acids are corrosive, bases are caustic. And that's what that would do to you. That would not be a fun thing, because then as you inhale that chemical, as you try to breathe, then it's going to start doing the same thing to your lung tissue. And that's when things really get nasty, as you're basically choking on your own dead cells and blood. Not pretty. But why is the Tide Pod the way it is? Because you know you can take one of those Tide Pods, toss it into the washing machine, fill it up with water, and it will clean the clothes still. How about Gatorade? Have you ever made Gatorade from powder? What's in there? How do you know how much Gatorade to use? The scoop tells you how much Gatorade to use. Or if you're making Kool-Aid, the scoop tells you. Everybody's figured out the scoop for you, right? They tell you how much water to add, how much to the scoop, all of this. The scoops told you this. What if you had too much water to one scoop? It's diluted. It doesn't taste as sweet, does it? Right. So if we have a chemical that we know the concentration of, and we add a certain volume of solvent to it, we do what's called diluting. But chemists they don't have scoops for everything. Chemists actually have to figure out, okay, if I have this concentration of this, I need to make this concentration. How do I do that? Well, they have to calculate basically the scoop or the volume of the solution to use. This is called the dilution formula. This S stands for stock, which is your starting solution. The D stands for diluted. All that's happening here is we're taking some stock and we're putting water with it, and we're getting a new volume and a new molarity. What I like to do is I usually put M1V1 equals M2V2. This looks more like our old pressure formula, P1V1 equals P2V2, that did pressure and volume. This does molarity and volume. Again, this is the stock and this is the final. So it says a chemist wishes to prepare 500 milliliters. They wish to prepare for that. Well, what is milliliters unit? Volume or molarity? Milliliters is a volume. And since she wishes to prepare that, that's V2, because that's what she wants to make. The molarity that she wants is 6 molar. So that's M2. But what is she starting off with? Well, she's starting off with 15 molar stock solution, which is M1. So what I need to figure out is I need to figure out how big that scoop is, right? I need to figure out how big that scoop is, or what that volume is of the initial solution I'm going to start with. So we got M1V1 equals M2V2. I'm going to divide both sides by M1 so that I isolate V1. M2 was 6 molar. V2 was 500 milliliters. And M1 was 15 molar. Now, a good question, a good student would sit there and say, well, that's in milliliters. Don't you need to have that in liters? Well, molarity is definitely moles per liter, but that cancels out here. So this will give me the volume of the scoop in milliliters if I continue now. I could always change that to liters if I wanted to, but I don't think it's necessary. So 6 times 500 divided by 1. No, not 1.5. 6 times 500 divided by 15.
The answer is 200.
So our scoop is 200 milliliters. We're going to start with 200 milliliters of the 15 molar, and we're going to add enough water to match 500 milliliters. Some of you might be saying, oh, don't you mean you're just going to add 300 milliliters of water? No, we never say that. We always say we're going to add enough water to make 500 milliliters. Because when it comes to solutions, sometimes 50 plus 50 does not equal 100. There is space between the particles. If I take 50 milliliters of water and 50 milliliters of alcohol, I'm not going to get 100 milliliters of solution. So just keep that in mind. That's why we'd always just use the term add enough water to reach 500. Easy enough. Take a second to get this problem right here. Exercise 3 done. I'll give you about a minute and a half. You need a drink. Got it? All right. So the chemist is preparing 500 milliliters of 3 molar. So she's preparing this. So this is V2, this is M2, and this is M1. Right? How should she prepare the solution? Well, M1 V1 equals M2 V2, dividing both sides by M1. We get 3 times 500 milliliters divided by 18. The moles per liter cancel out. 3 times 500 divided by 18.
It's about 83.3333.
We got two significant digits, so 83.3 milliliters of 18 molar with enough water to reach a volume of 500. Let's take a look at what this looks like in real life. So I've got this solution. It says it's 0.448 molar sodium hydroxide. Sodium hydroxide. I want 250 milliliters of 0.1 molar sodium hydroxide. Let's go ahead and figure out how much of this I need to start with. got the math on that. So we've got 250 milliliters times 0.1 molar divided by 0.448 molar. 0.1 times 250 divided by 0.448.
The answer is about 55.8035.
So we need 55.8 milliliters of that stock solution. We're going to add that to here. And then this is what's called a 250 milliliter volumetric flask. I don't know if you can see this line right here, but there's one line on this flask. That line is 250 milliliters. So that's where that is 250 milliliters full. Let's take a look here. Somebody remember that 55.8 milliliters for me? Got it? Two. Get off of this real quick. We're going to go with this camera here. All right. So here is my solution. This right here is a graduated cylinder. This is a volumetric flask. So let's show you real quick. I want to make sure I have a clean volumetric flask. And we always start with clean glassware. That's one thing about being a chemist is you usually spend a lot of time cleaning. And since we're dealing with concentrations here, we need to also make sure that we dry these out. Before I dry this out, I want to give it one big rinse with distilled water because tap water has things in it, right? Tap water has pollutants. So I'm going to get this completely drenched, clean, and then rinsed, and then dried of even my distilled water. So that's harder to do with the graduated cylinder. So let me show you the technique used for that. You start with what's called a glass stir rod. Have we done this before? Yeah. And you have your paper towel, and then you roll your paper towel along this. Now the key is to always make sure that you have hold of some of the paper towel. Otherwise, what can happen? The paper towel can get what? Stuck in that thing. If that occurs, make sure you get Mr. Jackson immediately because he has taken more paper towels out of there than you could possibly ever get stuck in there. But if you try to get it out, you may end up getting it stuck more. So, proper technique, I try to tell these guys every time, never pour from here. Always pour first into a beaker. I need 55.8. So I'm going to get about 60 milliliters with the beaker. I always get a little bit more. This beaker can give me no really good measurement. That's why I get about 60. If I get about 60, I'm probably pretty sure I got 55.8. Oh no, I didn't get 60. I got 50. We're gonna need a little bit more. I should have looked more carefully down here at this. There we go. 55.8. We're going to pour directly into here. There's 55.8. to make sure we don't have any bubbles messing with us. A little bit more. If I wanted to, I could use a pipette for this, but I just need about 2 more drops. Oh, 1 more drop. $55.8. All right. Set that aside, or in reality, probably just dump that out because I don't need it. And that's the thing, most people do that and then they don't clean this out. What's still in there? Some of that sodium hydroxide, right? That's why we always want to start with our own clean ones. We take our volumetric flask, we pour that in there carefully. Now we just need to add enough water to reach 250, right? Problem is there's some left over in here, isn't there? So one way we can get anything that's left over in there is we do a rinse of this container. Since my solvent is H2O and I need 250 of it, I might as well go ahead and fill that up and pour that in. So now I'm close to 150, right? I need to get up to 250. I'm going to pour around the edges here a little bit, and I'm going to pour this in as well. And what you're going to see is we're going to start to get to that neck, and that's when things get a little iffy. That's when I need to be careful. So I either use a dropper bottle or I use this. Make sure that's distilled water. And we take it right up to that mark. There's only 1 mark on here. So we get that right on the mark. And then we can cap this, tip it over, let it sit. There's my 250 milliliters of a 0.1 molar sodium hydroxide solution. So I'm going to get a marker and I'm going to write that on there. .1 molar sodium hydroxide. That's how a chemist would make that. Easy enough. Let's take a look real quick at something that's could be kind of cool. Here I have 1 molar of HCl and 0.1 molar HCl and 0.1 molar NaOH. Take a look here. This is Thymo Blue. This is what's known as an acid-base indicator. I'm going to put 5 droplets of that in there. 1, 2, 3, 4, 5. What color does that look like? Blue, purple, right? Let's take a look. I'm going to add 5 milliliters of my acid. See that? The acid I'm using is HCl. I'm going to cheat a little bit since I don't want to waste the time. I'm going to go ahead and pour some of that HCl in there, and that's going to flush everything out of there. And then I'm going to go up to 5 on this. Little cheat method to save from having to clean it. All right, there we go. We've got 5. What color are we now? Red. So what ends up happening here is an acid turns this thionyl blue red. And a base will cause that to turn back to blue. But here's the cheat. Last period I made 0.1 molar of the acid. This period I made 0.1 molar of the base. So if we take 5 milliliters of that base, that should neutralize that acid. Again, do a quick little cheat here. Clean that out the cheap way. And then add our 5 milliliters of the base. What do you think is going to happen? If we made these correctly, they should neutralize each other, and we get back to the blue. Pretty cool. All right, so today we learned how to make a chemical from a stock solution. Last time, we learned how to determine the concentration of something through evaporation. I think the major next step we have is to make a solution by using powder and liquid. So those are our goals. We're next, maybe by the end of next week or whatnot, we'll have somebody make those for us in class. Let's take a look at what your homework assignment for tonight is. So tonight you need to do 6 and 7 if you've not already done these, and these are not showing up for you to see, are they? Let me get those up so you can see them. There we go. 6 and 7 from page 8. That is using the molarity formula. And then 8 through 10 using M1V1 equals M2V2. We will have a quiz on Thursday. We'll have a group quiz. Is this our first group quiz? Yeah. Yeah. So we'll have a group quiz on Thursday and an individual quiz after that group quiz on Thursday. Just so you know what you're prepared for, when you do it with a group, I'm going to pause the recording. When you do it with a group, you actually have to know the naming as well. So you can see it says group molarity quiz 1 naming. So what that means is, take a look at this problem here. It says you wish to prepare 50 milliliters of 0.5 molar potassium carbonate. You will not be given this. You will be given the name potassium carbonate in your group. So somebody from your group will have to sit there and go, okay, that's K with a +1 charge. That is CO3, that's a polyatomic ion. Does anybody know the charge of carbonate? -2, good. -2. So how many +1s do I need to balance 1 -2? 2 +1s, right? So the 2 potassium and 1 carbonate. Why is this a big factor? Well, on this problem right here, you need that to count up the mass of it, which they've given you. I will not be giving you that for the quiz. Just keep that in mind. The quiz will be more like the problems you're doing tomorrow on page 9. But these problems are easier on this page, so they work you into it at a slower pace. That's the idea, right? We know that chemistry, each unit seems to start off rather easy, where we just talk about things and we're like, oh, this thing's saturated. And all of a sudden, boom, it's math, and you know, stress levels get a little bit up. That's why it's important that even when it seems easy, you pay a decent amount of attention. All right, that's all I've got for the day, guys. If you have questions, by all means, stick around. Otherwise, have a great day.